Let's talk about how sound travels. Specifically, what I want to do is go over the physics of how it is that sound gets from my mouth to your ears. Well, in order to do that, let's start off by imagining that you and I, we're in the same room right now, just having a conversation. So here's me, here's you. Give you some ears so you can hear, all right? And somehow, sound waves are getting from my mouth to your ears. Well, how's that happen? How's that work? In order to understand that, we're going to have to talk about air. Well, here's the challenging thing, is we're both willing to believe that the room is full of air, but we can't see it. It's invisible. So we need some way to get some insight. The way I like to do that is, if I clasp my hands together, you can imagine that's a small volume of air. But again, it's invisible. You can't see it. So to help with this, I like to use tennis balls. I think of tennis balls as little volumes of air, and I'll just use those two words interchangeably now. So this represents a volume of air, and we said the room is full of air. So what I need you to visualize is imagine filling the room with tennis balls. I mean, floor to ceiling, wall to wall, front to back, full of tennis balls. Let me try to draw that. So you and I were in a room, and it's just full of tennis balls. I'll draw some big tennis balls just so I can fill the room up quickly. But front to back, floor to ceiling, tennis balls everywhere. In fact, you can't see me because of all the tennis balls that are in the way. If you can imagine that, that's terrific, because this is the physics of sound. Anytime you have a question, think back to this analogy, and you'll get the answer right every time. So we need to talk a little bit about the properties of air. And there's two things we need to understand. Air has spring and it has mass. So we'll start with spring first. If I compress this tennis ball, you can see it squishes. It has some spring to it, though, because it wants to come back to its original shape. It's actually quite a bit of work to hold the tennis ball that compressed. It wants to come back to its original shape. And you know this. Look, if I had a balloon right now and you squish it, it wants to come back to its original shape. If I expand it, it wants to come back to its original shape. It's a property of air that it has spring. The second property, I'll let you kind of observe here. If I let go of the tennis ball, it drops. The reason is the tennis ball has mass, gravity acts on it, and it falls. Well, similarly, air has mass. And this is interesting. If I have a box of air, you think of a box of air here, a meter by a meter by a meter, it has a mass of a little over 1 kilogram, so a little more than about 2 pounds. Well, what's interesting about that is, let me demonstrate to you this incredible feat of strength. Ta-da! Imagine we were outside right now. Above me is a box of air, has a mass of 1 kilogram. Above that is another box of air, mass of 1 kilogram, all the way up to the sky. I'm holding up hundreds or thousands of kilograms of air. How am I able to do that? Well, go back to the analogy. The room's full of tennis balls. It's a sea of tennis balls. So am I really holding up all those tennis balls, or am I sort of just putting my arm into a sea of tennis balls? You may have actually done this. If you've ever played in a ball pit where you can dive in and sort of run around, it's great fun. If you put your arm in there, you don't feel the crushing weight of all the balls above, because the balls to the front, to the back, sort of hold up all the adjacent balls. So you sort of move the balls out of the way to get your arm in there, but you don't feel the crushing weight. And that's what's happening when I put my arm out. There is air above, but there's air to the sides and below that's holding up all of that air mass. So I don't feel it all. So these two properties, spring and mass, what that means is that air can store potential energy in spring, and when it's moving, because of its mass, it has kinetic energy. And what we'll see is that sound waves are actually the interchange, the exchange, the continuous exchange of potential energy to kinetic energy to potential energy to kinetic energy, and that's how sound's going to travel. So now we can get to the heart of it. As I'm talking, am I throwing tennis balls to your ears? And are you then, when you answer, you throw a tennis ball back to me? So if you and I were in the same room right now, would you feel all these tennis balls whizzing by your ears? Well, clearly not. You're used to talking to people and you don't feel the tennis balls whizzing by. Something more complicated has to be happening. And of course, there's no way for me to throw a tennis ball from my mouth to your ears because there's no clear path. You can't even see me, remember, because of all the tennis balls. Well, I can't fill the whole room with tennis balls, but I can fill this tube with tennis balls. I want you to imagine it's your mouth over here on the left, my mouth over here on the left, sorry, and your ear over here on the right. Well, as I'm talking, what I'm actually doing is I'm pushing the tennis ball, which causes the rightmost ball to move in kind of a chain reaction. Let me do that again. 1, 2, 3, push. You can see the last ball moves. 1, 2, 3, push. The last ball moves. So it's this interesting chain reaction where the first ball pushes the second ball, which pushes the third ball, and so on, down the chain to your ear. And if we could kind of zoom in on that in slow motion, what you'd see is that what I'm actually doing is when I'm push the first tennis ball, I'm actually squishing it, I'm compressing it. That opens up a gap between the first ball and the second ball. So then the first ball moves over. So we have squish and then it moves. But boy, it's a lot of work to hold this tennis ball right now, compressed. It wants to expand back to its original shape. When it does that, it's naturally going to compress the next ball. So the first ball went squish, moved over, expanded, which causes the second ball, when the first ball expands, to squish. And again, now I've got a gap between the first ball and the second ball and the third ball. It moves over, expands, squish, the next ball, moves over, expands. So this squish, move, expand, squish, move, expand, squish, move, expand, that's the chain reaction that carries sound from my mouth to your ears. And let me be really clear, no tennis ball actually travels from one end to the other, just the squish, move, expand. Now, if you look very carefully, and I do this 1, 2, 3, push, there's actually a very slight time delay between when I push on the first ball and when the last ball moves. And that's the speed of sound. You may have learned at some point that the speed of sound is pretty quick. It's 350 meters per second. Let me write that down. 350 meters per second. I like to get some physical intuition when I see a number like that. So maybe this will help. Think about a soccer field. A soccer field is roughly 100 meters long. So imagine I have one soccer field, followed by a second soccer field, another 100 meters, followed by a third soccer field, 100 meters, and I kind of have a half a soccer field, so a 50 meters. So in 1 second, sound travels 3.5 soccer fields. Again, let's put some intuition behind that. Suppose I had you, and we're going to have you race sound. So the starter pistol is going to go off, and we'll see how far you get in 1 second versus sound. So starter pistol goes off, you take off, you start running. In 1 second, sound goes 1, 2, 3.5 soccer fields. Wow, really fast. You might get, I don't know, about 5 meters. Okay, barely, you barely make any progress at all. So sound is much quicker than almost everything we experience in everyday life. Now, there are things that go faster, and in one of our later videos, we'll talk a little bit about that. But next, what I want to talk about is in this cascade, this chain reaction between my mouth and your ears, what I've been doing is pushing the tennis ball. Well, it turns out what your ear is actually sensitive to is vibration. And I want to explain how vibrations travel from the left-hand side, my mouth, to your ears.